Hello and good day, geometry. We are covering PO36, which you should recognize some of the things that we're talking about here. You see the three letters SSS and SAS that should bring back, no doubt, fond memories of side, 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 and side, angle, side, in proving that triangles are congruent, which is kind of what we're doing today, but instead of congruency, we're going to focus on similarity. So we aren't going to be writing full-fledged proofs like we did before, but we're going to be recognizing and learning how to use three different theorems to prove that triangles are similar. Yes, sir?
Do you have a pencil?
No, they don't trust me with one.
Okay.
Yeah. So just to review a little bit first, similarity. What does it mean for two triangles to be similar versus congruent? Elise?
They have the same proportion.
Right. Similar triangles are proportional, okay, whereas congruent triangles are the same size and the same shape. They're equal. They're congruent. So there are more theorems to prove congruency than similarity. The three that we're going to talk about are angle, angle, side, 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 and side, angle, side. Okay. So the angle, angle similarity postulate says that. We should do our wrist exercises first because there's a lot of note taking today. So writing hand up in the air, forward, backward, round and round. No complaints about soreness. We're ready to go. If two pairs of corresponding angles are congruent, then the triangles are similar. The angle-angle similarity postulate states that if two pairs of corresponding angles are congruent, then the triangles are similar. Why don't we need all three pairs of angles? Why is it not AAA? Why do we just stop at angle, angle? Why not all three? Evan?
Because if the two angles are congruent, then the third one has to be.
Very good. If two pairs of corresponding angles are congruent, the third pair has to be. Anyone remember the name of the theorem that states that? Because you're right, that's the theorem, but anyone remember the name of it, just off the top of your head? It's the third angles theorem, okay, the third angles theorem. But we apply it here, okay? So if we've got two triangles, and I'm going to try and make these somewhat similar here. We'll make one bigger than the other. There, we'll try and something like that, perhaps. Okay. If two pairs of corresponding angles are congruent, so let's say we've got one pair here, another pair here, we can say those two triangles are similar. Okay. Now, which means again they're proportional. Clearly, they're not the same size, right? They are proportional. In your homework and on the test, it'll ask you to write a similarity statement. A similarity statement looks like this. I'm going to label these points A, B, C, and D, E, F. Okay. And we've written congruency statements before. So a similarity statement will say that triangle ABC is similar to triangle DEF. And that symbol for similarity is that same little curved thing that goes above the congruency symbol, okay? But without the equal sign, it just means similar to. So that would be a similarity statement. Question so far? Good? Okay. The side-side-side similarity theorem states that if the three pairs of corresponding sides are proportional, then the triangles are similar. If the three pairs of corresponding sides are proportional, then the triangles are similar. The side-side-side congruency theorem would say that the three sides are congruent, right? but here we're talking about similarity and proportionality. So again here, let me try and draw two similar triangles. One a little bit smaller than the other. Okay, we'll label our points A, B, C, and D, E, and F. And side, side, side here has nothing to do with angles. We're only going to be focused on the side lengths here. And let's say that we've got a side of 5 and 3. And then let's go 12. Oops, wrong triangle. 20 and 12. And 30 and 18. Okay, clearly not drawn to scale as I look at this now with my, in fact, is this even a legitimate triangle? No. Clearly I did not plan ahead for doing this one. But yeah, and the reason why it's not a legitimate triangle is because some of two sides, 5 and 20, don't, but for the purposes of what we're talking about, it's going to keep it the same here. Okay, so we got side lengths of 5, 20, 30, and then 3, 12, and 18. How can we determine whether or not these three pairs of corresponding sides are proportional? What are we going to do to make that? Yeah.
You can grab all three numbers and put the same sides and a fraction.
Sure. And how do we know which side belongs with which? It's easier when the triangles are kind of positioned the same way as they are here, but if they weren't, how would you determine which side goes with which? Like Sebastian's saying, let's put this 5 and 3, write that as a fraction. How do we know that 5 and 3 go together? Elise? Same order, so you can look at the order in which the similarity same is written, or they're the two shortest sides, okay?
Angles?
If you're given information about angles, you can take a look at that also, okay? But you have to make sure those sides correspond. In this case, it's probably easiest just to look at, since they're positioned the same way here, 5 and 3 are in the same spot, and 20 and 12 would go together, and 30 and 18 would go together, okay? And what you're looking for are these three fractions equal? Give me a couple different ways that you could make that determination. Elise, give me one.
You could simplify the fraction.
Sure. 5/3 is in simplest form, but 20/12 simplifies to be 5/3, as does 30/18. That would tell you they're all equal. It would tell you that these two triangles are similar. What's another way you could determine whether or not these are all equivalent fractions? Yeah. Lucas.
Oh, I wasn't.
Yes. That wasn't a hand up?
No, that wasn't.
Are you giving someone a high five? What do you want? Sebastian.
They start out like this.
Well, this is what I
then
normally
move
do.
my head.
You can see that 3 times 4 equals 12, 5 times 4 equals 20, and then 3 times 6 equals 18, and 5 times 6 equals 30.
Sure, you can use scale factor, right? 3 times 4, 5 times 4, 3 times 6, 5 times 6. Scale factor is the same. What else could you do? There's one I'm waiting for someone to say. Julia. Right, you can compare decimals, okay? And these are pretty easy fractions to work with, but if you have more complicated ones, decimals work great. If these three fractions are equivalent, they're going to have the exact same decimal value. But anyway, we can say that these two triangles are similar because of side, side, side. All right? The last one is side angle side, and this one says, if two pairs of corresponding sides are proportional and the included angles are congruent, then the triangles are similar. Whew. All right. If two pairs of corresponding sides are proportional and the included angles are congruent, then the triangles are similar. So again, let's draw a couple triangles here. Put the smaller one first this time. There we go. Okay. We'll say this one is 3. This one is 7. This one is 9. This one's going to be 21. And we've got the included angle congruent. That would be an example of the side angle side similarity theorem. Okay. Give me 2 ways that we can prove that those 2 sides, those corresponding sides, are similar. 2 ways that we can do it. Sebastian, one. Give me 1 way we could set up a proportion. How?
Do the same sides. Do 21 over 7 and 9 over 3.
So 21 over 7 is equal to 9 over 3. What's the other way that we could set this up? Sebastian kind of went from the big triangle to the small one. 21 over 7, long side over long side, then short side over short side, 9 over 3. What else could we do here? Grayson?
You could do shorter or smaller triangle to the larger one.
Right, we go the other way. We go 9 over 3 equals 21 over 7. Okay, we could flip that upside down. So it's 7 over 21 equals 3 over 9. There's one other way that we could set this up. Daniel? Well, we can't really get a decimal until we get the proportion, right? Now we can see that, 21 divided by 7 and 9 by 3, they're both 3. But what could we set up? Elise?
7 over 3.
Right. The other one we could set up is 7 over 3 equals 21 over 9. Okay? And we would see that those decimal values, or if you simplify 21/9, it simplifies to be 7/3. Remember, you can go from one triangle to the other, or you can stay within the same triangle and set up your proportion that way, whichever one's easiest. Both will work. And the reason why both of these work is because, we can also use cross products to determine whether or not these are equivalent fractions. And in both cases, we're multiplying 7 by 9, right? And then 21 by 3. So since that relationship exists in both proportions here, both are valid. And then, of course, that angle that's included, okay, it's the angle formed by the 2 sides that we have, has to be congruent. Questions on any of those 3? I don't know about you, but this is feeling like a great video today. Greatness achieved. You make me nervous. Okay. For each of the 3 examples below, show how the 2 triangles are similar. The first one here, triangle ABE and ACD. ABE is smaller triangle that's actually inside the larger one. Is this set up for angle, side, 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 or side, angle, side? And be prepared to defend your answer. Evan?
Angle.
How so?
They give 52 as congruent angles, and then they share the top angle.
Yes, okay. So one angle is given to us as congruent, that 52, but then the second angle, angle A, is actually an angle of both triangles. So because the reflexive property, where we use that a lot with proving triangles are congruent, is again here to say that angle A is congruent to itself. Therefore, yes, these triangles are similar because of angle. Okay? And even using logic here, before just looking at the diagram, why would you kind of assume it's going to be angle? What is it missing that we'd really need, Sebastian?
Like an actual side measure.
Yeah, if you're given no side lengths whatsoever, it's going to be pretty tough to get a side, or side angle side. Okay, so you can kind of use the information provided. Like this next one here, you're given 2 pairs of sides. Maybe we could do something to find the third side, but what do you see here? Audrey? Okay, so angle ACB here and angle ECD are congruent because of vertical angles. It so happens that those 2 angles are the included angles of the 2 sides that were provided. So now we need to figure out, are those side lengths proportional? Give me one proportion we could set up that would be valid for us to make that determination. Grayson. 9/18 is equal to what? 15/30. That's valid. Give me another one. Sebastian.
9/30 and 50. Oh. I got, sorry, never mind.
This one's a little bit tougher because the triangles aren't positioned, the same, right? Lucas?
18/9 is equal to 30/15.
Okay, we could flip this around. 18/9 equals 30/15. So these two proportions kind of stay within the same triangle. But let's go from one to the other. Alex. 15/9 equals 30/18. Of course, we could flip that around. 9/15 equals 18/30. And what do all of these have in common? The position of that 9 and 30, if we were to use cross products, right? We'd be multiplying those together, and the position of the 18 and 15 here. Okay? The reason why it's not 18/15 equals 9/30 is because the way these triangles are positioned, right? This one has been kind of flipped over. Okay? So if you compare short with short and long with long, that's why the 9 and the 15 go together there, and the 30 and the 18. 9 and 15 are both the short sides of that triangle. 30 and 18 are the long sides. So, long story short, are these two triangles similar? Yes. Because of side, angle, side. After this is now 14 years of teaching, I realized that I must laugh at my own jokes because no one else might. And if I laugh at my own jokes, sometimes I can't tell, I can't hear whether or not people are actually laughing. So it's just a self-esteem booster. I'm assuming that you're laughing. I'm assuming it. Okay? I do make terrible jokes. I'll admit that. The last one, find the value of x that makes triangle ABC similar to triangle DEF. So again, here's an example of a similarity statement. And we're looking for what value for x makes that happen. Okay. What do you think? What is a proportion that we could set up and then solve that's going to give us a value of x? Julia? You could. I'm not going to advise it though, because as you look at this, and the method that we need to use here is probably cross products. Whenever we have a variable cross products, works really well. What are you going to get when you use cross products here? That right now is a little bit frightening, but in about a month won't be because we'll have covered it in algebra. Elise?
Like 3x plus 1 will be multiplied by x minus 1.
Yeah, we haven't talked about really how to multiply 3x plus 1 by x minus 1. You might know, okay? But then the process to solve it, once we get that x squared, we've created what's called a quadratic equation, okay? And the methods for solving a quadratic equation, we start talking about that in, I think, PO53 or something like that. So it's coming up, but we're not quite there yet. So anyway, the point is, this would work, but mathematically we're not there yet. So what's another one? This is right, 18 over x minus 1. What's the other half of this that we could use that doesn't involve that other x term? Julia, why don't you finish it out? 12 over 4, yeah. If we don't have to use both x expressions, let's not. Just makes your life easier, okay? And again, when you solve this, I'll caution you, we had this in an earlier objective, that 12 times x minus 1 is not going to be written as 12x minus 1, right? Because it's the 12 times the entirety of that expression. That x minus 1 needs to be in parentheses, okay? And then 18 times 4, 72. And raise your hand when you have a value for x. While we wait for those to finish, who would like to hear a knock-knock joke?
Oh, no.
Oh, boy.
I've been eating.
Julia, do you want to hear a knock-knock joke?
Sure.
Okay. Knock-knock. Owls. Yep.
Oh man. I got that right as you were like, I
Oh,
was
I get it.
Get it? Owls who? Yep. Yep, they do.
Nobody's really said it.
That's funny. You should. No? Okay. What value did you get for x here? So I had for 7. So x equals 7, and we can plug this in, check it out. X minus 1 would make this 6, which falls right in line with our other proportions. This one, 7 plus 1 times 3 gives us 24, which falls right in with our other proportions, and so we're good to go. Okay. Questions on anything from PO36? Okay. Your assignment is again from the textbook, and I would like you to do, I forgot what I gave the other class. Uh-oh.
Hopefully something easier.
It is soups easy.
What does that even mean?
It's short for super, which really isn't any shorter at all, but that's okay. I'm just trying to be hip. Page 392, 5 through 12. It's 8 actually.
You ripped it.
And no, I think that's all I gave them. Just 5 through 12. Oh wait, no. Hold on. Hold the phone. I gave them more. And going back actually to page 384, I had them do 9 through. Yeah.
Dude, that was a better class.
There you go. And it's not due until technically our next live class, which is next Tuesday. So you've got like a week to do it. All right. You've got time worked now if you want to stay until 2:45. If you need to bounce, you may go. But I can be here for assistance. Any questions, comments, concerns, complaints, comments, congratulations, or criticisms?
How do you memorize all that?
I've said it for many, many years. All right, if that's all you have for me, that's all I have for you. That's how you math.
Don't forget to like and subscribe.